speaker is Michael Cafarella. He's a principal researcher scientist at an MIT Computer Science and Artificial Intelligence Laboratory. Cafarella's research interested including database information extraction, data integration, and data mining. He has published extensively in venues like SIGMOD, VLDB, and elsewhere. He received his PhD from the University of Washington, Seattle in 2019 with advisor Orden Etzioni and Dan Suju. His academic awards include NSF Career Award, the Sloan Research Fellowship, and the 2018 VLDB 10 Years Best Paper Award. In addition to his academic work, he co-started with Doug Cutting Hadoop, an open source project which is widely used in Facebook, Twitter, and elsewhere. Yes. Let's do an applause for our next speaker.
Thank you very much, everyone. All right, great. So today I'd like to talk to you about a relatively new project, which is on the topic of building a shared conceptual model of today's complex and heterogeneous data systems. I think there's going to be a lot of connections to at least the previous couple of speakers, so hopefully we'll find it all interesting. Okay, so data management in the good old days was pretty basic. There was one thing called your database. You had a bunch of users who you probably employed, and they added data that you owned to build reports or bills that you sent to your own customers. So that thing in the middle probably cost an awful lot of money, but it was a pretty simple time. Of course, nowadays, the world is a lot more complex. Even in a single organization, we have a vast array of data tools. And more than that, we are constantly sharing, ingesting, and publishing data in whatever form, whether that's a database, a visualization, or some data-derived product with a range of other people, other institutions, individual users, or maybe people on Facebook trying to either support or debunk what we just published. So one big challenge in all of this work, something that we at least partially addressed in the old days of a relational database being the center of our data management activities, is the problem of shared metadata or shared conceptual models for what's happening. Nowadays, when we are constantly publishing data, meaning between tools, even within a small team, or between teams in one organization, or between institutions, this problem of transmitting metadata, the comments, the rules that govern the data along with it is omnipresent. So relational schemas, they're great, but they're basically limited to those traditional RDBMSs, which nowadays are a small fraction of our overall data activity. XML has been posited as one approach, but it's not widespread. Documentation, okay, it's great when you have it, but it's often incomplete, either not good enough for the task or just there isn't any. And data catalogs, which have become popular recently, are very expensive to populate, and they're pretty limited in reach. A lot of people don't adopt them internally, they don't go across institutions and so on. And unfortunately, in the data management world, the sharing primitives we have for data, in the absence of this kind of metadata, are pretty weak. It's not like shipping an API or a traditional library where there are compile time checks, where correctness is relatively easy to check. Oftentimes, when we ship a data set to someone, the consumer of it doesn't know there's a problem until they're far beyond the end of their processing. That data quality checks at the endpoint are really the only way we have of checking whether our inputs were any good. What this means is that anyone who's concerned with the semantic side of data management, whether you're a data scientist, whether you're writing governance rules for your organization, or you just want to be an informed consumer of data, you constantly fall over this kind of semantic management obstacle. If you're a data scientist, I mean, there's constant bickering, productive bickering maybe is the way to say it, over what is the definition of a certain column or a certain row, what's the standard for correctness of your data set. Governance is frustrating because you can't actually write rules that apply uniformly across a lot of data sets. And even just being an informed data consumer, wondering what does the x-axis mean in this visualization that someone put into a PowerPoint deck, even that's often difficult to know. And even if you answered it, well, the next version of the PowerPoint deck or the person who's using the same visualization inside a different document is not going to benefit from your conclusions. So we're really failing all sorts of different user communities when it comes to the metadata management of today's very heterogeneous systems. So, our modest proposal here is we want a single universal model of every single data set in the world and every single data process in the world. That doesn't seem so tough, right? Well, okay, seems actually kind of stupid. If we could do that, why haven't we done it yet? It seems like schema management, which is known to be really difficult, but enormously harder. So how could we possibly think this could work? Well, for a moment, put aside the how and focus on the why. If we had it, it would be great, right? Imagine a universal catalog of every single data set you ever used, whether you generated it or whether a colleague generated it. Well, if you're a data scientist, you can check to see, does this data set conform to well-known standards? I could also check, did they use a particular well-known visualization function, or is it something that the student wrote at 1 a.m. that morning and maybe deserves a little bit more examination? If you have data governance rules, you can write them according to like reliable interinstitutional provenance. And even just as a data consumer, you can look at a visualization and you could reliably know in a trusted way, what's the x-axis or the y-axis? How was the data generated for this particular visualization? Now that's a serious challenge. When you look at a visualization, who knows how many steps preceded you between the collection of that data and the actual production of it? Well, as someone who, with my students, every day is basically looking at different reports of visualizations and asking questions of it, there's incredible amounts of latency and difficulty involved. Hey, how did you generate that data set? Well, let me go to the Python script and check it out. But there's lots of questions that we would love to be able to answer, but most of the time we can't, or if we can answer them, it involves sending an email, waiting for a response, or maybe hoping that someone who made the data set 2 years ago gets back to us. Okay, building this thing would be great, but of course it doesn't seem easy, so how can we possibly do it? Well, we're going to shift the goal a little bit. Instead of a traditional schema that governs anything, we're going to instead build a massive descriptive shared data set, something that doesn't necessarily guide you. It's not going to be like a relationally enforced schema, but it could guide you if you wanted to. That's a little bit easier, and the good news is we can do that. The thing I want to talk about for just a moment is this idea of a knowledge graph. Knowledge graphs like Wikidata have been an enormous boom in the data management world in the last, say, 8 to 10 years, but they're not generally appreciated. And I want to be their cheerleader for just a moment, because they're going to give us an existence proof of how maybe we could build this shared model. The best known knowledge graph is Wikidata. This is the structured part of Wikipedia. If you look at, say, the Barack Obama page on Wikipedia, there's a bunch of text about him. And in the right-hand column, there's facts: spouse, date of birth, place of birth, and so on. They come from a graph structured database called a knowledge graph. And that knowledge graph, Wikidata, has really grown a lot in the last few years. What's really remarkable about it is that these knowledge graphs have been able to obtain enormous scale with high quality metadata throughout. It doesn't show the kind of degradation of metadata that you might expect in a relational setting. And even more excitingly, you can build them with a scalable curation budget. It does not take increasingly super linear numbers of humans to curate it just to get to something good. Let me give you a little bit of background stats on the growth of Wikidata. Here's the growth in the fact count of Wikidata. In the left-hand side, you have 2014, there were about 53 million facts. In the right-hand side in 2020, just shy of 1.2 billion. The color code here shows you what kind of data is in there. One weird thing about a knowledge graph is that it mixes traditional relational data style facts with metadata, bibliographic citation data, and so on. You can see which subset here has been growing more rapidly, but basically all categories have been growing over the years. Here you can see who does it. It's a mixture of software and kind of super editors, people who do many edits. It's not a whole lot of like one-off, one and done kind of editors. And here you see the number of edits per year. This is the number of times someone tweets something in Wikidata. Now, is this good or bad? I don't know, but what you can see is that the growth is not super linear. As we put more curation effort into Wikidata, we're getting a better data quality set out the other end. This is what's really exciting and is maybe what should make us optimistic about building this shared model of all our data management work. Okay, a little bit of background. An entity, Barack Obama, MIT, Cambridge, that's a node in this graph. A property is an edge in this, a directed edge in this graph. Every entity in the world has a unique identifier. So Barack Obama is Q76 in Wikidata. If we were to build the data management version of this, maybe your visualization that you're looking at right now would be X9999. It has a unique identifier. just like every web page or every object in Wikidata. An edge type here has a semantics associated with it. So it might be instance of, Barack Obama is an instance of human. It might have the date of birth relationship and so on. And statements of fact and schema are mixed together, as I mentioned. I'm going to skip that for a moment. What I want to emphasize is that certain quality metrics that are challenging in the traditional database world, even when we have professionals curating them, are remarkably good in Wikidata. So deduplication of entities, you don't get 36 different versions of Barack Obama. You don't get 5 different versions of the spouse relationship. The quality here is remarkably good. And the way they do it is really interesting. Instead of a traditional top-down database administrator, instead we have an editing interface, a piece of software that's constantly doing auto-suggest. You might want to type in a new kind of property, but boy, it's going to do some really strong popularity-based pushing of existing entities. In many ways, the interface is not designed to be correct, but rather is simply designed to drive consensus. That's an interesting slight tweak from what traditional schema management tries to do, and I think it's a really important one for seeing how it works. Finally, adding new data is easy. If you want to add a new fact, go ahead and do it. There's limited scrutiny. But if you want to add new structural elements, a new type or a new property, that gets thrown into a social process that involves a lot more human investigation. Okay, so what's our plan now? We're going to use this Wikidata curation model, a graph that anyone can extend, but with software that drives people to conformity as much as possible, and use it to try to model all of our data sets and our data modeling processes. As I said, it's going to be descriptive, not prescriptive, but practically speaking, we're hoping to drive conformity through kind of power law, rich get richer style dynamics. You might regret those on the web or in, but in a world of schema management, when standardization and conformity is great whenever possible, we're going to be happy that we have this. In short, we want to use the system to build what we call like a broad but flawed consensus of what everyone is doing and how they're producing their data. All right, this is a large project. It's been going on since last year. It involves a lot of people, including many people here, a bunch of people at MIT. I'm happy to talk more about how great they are after this talk. All right, so let's look at the demo. And could I ask how much time left before the talk? About 10 minutes or so? Okay, great. All right. So here what you should see is a page that in some ways looks like a Wikipedia page. This is a web page that represents a data object that we know about in the system. In the upper left-hand corner, it says 2016 court cases, all districts, object X27. This is a database. It describes all the federal court cases in 2016. And although it's hard to see here in the room, in the upper left, we've got the unique identifier. We also have the person who uploaded it. This is a colleague, Andrew Paley at Northwestern, who's on a project that uses science to investigate how the judicial system works. If you look at the actual content of the database here, you can see what the district name is, the case number, whether it's a civil or criminal case, and so on. Okay, so far so good. This is an object that has a unique identifier that's good no matter where you are. So no matter what institution you're in, you can always refer to this database uniquely by this X27 identifier. Here you can see an analytical result that came from that database. So this is for every federal district in the state of New York, there are 4 of them. What's the average case duration in terms of days? What we can see here is that the Southern District has an average duration of 196 days. The Western District has an average duration of 311. It's a pretty big gap. If you're interested in judicial sort of governance and management, you might be very interested in that result. Is it because one district has harder cases than the other? Is it because one is well funded and the other is not? Who knows? What's notable here is that this was created by a different user at a different institution. But despite that fact, we still have a reliable provenance graph that links them. So here at the bottom, we have a node that represents the current analytical result. This was the result of applying a SQL query to an intermediate data set of just New York court data. It has its own unique identifier. And it, in turn, was derived from that original database that I showed you first off. Okay. Now, we don't just have data sets in here. We can also have functions. So here's a choropleth map function that uses so-called FIPS codes. That's the way the Census Bureau numerically identifies a unique county in the United States. And we can use these objects that represent functions and pieces of code, apply them to other objects in the system, and get yet more data objects. Now, this might seem like everything's spiraling out of control, and our answer to that is that's just fine. In the web or in other online social systems, we generally have a system where everything can be uniquely identified, a small number of objects end up being important, and the vast majority end up, maybe rightly so, lost in obscurity. That's the same kind of design goal we have here, which is allow the creation of data sets and functions and data-derived products to be very permissive and rely on social processes informed by this kind of unique identifying and rich get richer online social property to drive implicit standardization among users. Finally, we have a visualization generate from that. So this is just a heat map or a choropleth map based on those duration numbers that I showed you earlier. If you receive this as an analyst, you might wonder, boy, that the color for the Western District of New York, it seems really high. Was that an error in the visualization? Was it an error in one of the joins necessary to produce the visualization-friendly data? Was it an error in the query that someone wrote? Or does this actually reflect real life? That kind of question, that kind of investigation, maybe not so dissimilar from some of the questions that were mentioned in Arvind's talk about COVID skepticism. What's maybe different is here you can look at the output and trace back what actually happened. So here we have the final output, that visualization map. In the upper left-hand corner, you have that analytical result that I referred to earlier. And then along the right-hand fringe, you can see all the external data sets we had to marshal in order to get to this visualization. So whether it was the judicial districts by county, the actual FIPS codes, or just the mapping of a FIPS code to a unique polygon on the screen, all of these data sets, which all come from different institutions, are now available to the end user. So in the earlier system I mentioned, one gets a report, it's embedded in a PDF. If you have a question about it, there's nothing you can do. Our goal is any kind of data result you see, whether it's an image, a database, or some kind of analytical result, it's always tied to an interinstitutional provenance tree that lets you trace back and answer interesting, relevant questions without calling someone up or hoping that you can get them on the phone. Okay. Let me stop here and jump back to the presentation. Okay. Now, one thing I want to mention, Tamer co-founder Mike Stonebreaker and an MIT colleague, he sometimes talks in the kind of data metadata management world of the schema bully, that sometimes you can avoid problems of schema management when there's one person who has so much market or institutional power that they can dictate terms to others. Here's a kind of classical Atlas mail-away cartoon about bullies. Okay, this guy, he takes some, he sends $1 in the mail, gets the Atlas program. Now he can bully the bully himself. Replace Walmart or Ford or whoever has a strong supplier relationship here, and they can play that role of a schema bully with others. Well, I say this, somewhat in jest, but there's a grain of truth to it. In the high-tech world of the internet, we've evolved past bullies. Now we're going just straight for schema mobs. The point here is that by creating some kind of force that can actually, in a soft way, dictate terms to others, that can encourage certain kinds of standardization. Imagine that we go back to that provenance graph from earlier. It'd be quite easy for us to see who was using which data sets to flag the data sets, the nodes in that graph that were more popular than others. Basically, something akin to PageRank, but for data sets and functions, so that you could be alerted, is the data product I'm looking at right now, is it something that has been fueled by only widely accepted data sets? Or is it something that's largely fueled by things that are idiosyncratic, whether that means they're not widely used or they're only used in a kind of sharing or social context that I disagree. In some ways, we're saying that this kind of trustworthiness and schema accuracy is socially defined. I think that's inextricably linked to this idea that investigating data and coming up with decisions is a social process. Okay. One way to view schema management is as a social coordination process. And these kinds of online mob style behaviors are one way of obtaining that kind of social coordination. Okay. All right. Let me mention a little bit about the technical work that's going on here, and then I'll stop and we can answer questions. So the system that I showed you right now, that kind of web system where there's a public interface, there's dedicated storage, and containerized execution of functions so that we can get a reliable provenance link. That's all done and working today. You can download it if you like. Regarding data construction, that's great. We're very proud of the system we've built. But in many ways, we feel it's a little bit too similar to data catalog systems nowadays. Data catalogs, they're okay, but they require a huge amount of curation and investment by organizations, which may not be even used within an organization, and certainly not every org out there is going to put in the same level of commitment. And yet the value of the system that we're proposing really comes from its universality. So one thing we're trying to do is build a graph that is much lower in terms of the hurdle of work, and yet might have lower quality semantics. Maybe we don't actually know what function you executed to go from data set A to data set B, but we know that A was used to derive B. That'd be good enough for certain applications. So we're building tools maybe akin to a daemon or a Dropbox piece of code that implements this kind of scan, extract, and improve cycle where we can populate a lot of that graph without direct human intervention. Data set search, we have basic keyword search right now. We're also using various embeddings of relational style data to enable much higher quality data object recommendation so that if you have a data set, we can tell you what are the best functions to apply to it, and we can include a healthy popularity element, again, to try to drive consensus among data set users. And then finally, there's applications that really fall into these data science, governance, and informed use scenarios. All these are kind of prototypes in the works right now. All right, so I hope I've been able to convince you that not only could we really use this shared model, but there's a legitimate path to building it all together. And if nothing else, go check out Wikidata. It's an unsung, exciting story. All right, thank you very much, everyone.
Thank you. Thank you, Mike, for the great talk. I think we have time just for one question. Is there anyone from the audience?
Fantastic talk. Regarding the comments of cataloging and how expensive that is, I think what's really compelling about Wikipedia did was create a system that allows for low barrier to entry crowdsourcing. And do you have a model within the framework that you're thinking about to have kind of a similar economy of scale of small, like micro curation type tasks of data?
That's correct, yeah. The current hypothesis on how that's going to work, we don't have it burning up the internet just yet, is if we can use automatic instrumentation to simply find connections between different data sets, if we can automatically detect A is a copy of B, or even A is a predecessor of B, like if that file is a log structured kind of thing, then establishing that chain of causality between one and the other, that's a great first step, because all it takes is one person to annotate it in order to be used. If we have a file that's been distributed among lots of different people, one person gets up and decides to make the world a little bit better, everyone can benefit from it right away. It's all in an aim to kind of kick off a cycle where people start demanding that their upstream data providers annotate their inputs a little bit better, because otherwise I can't get anything done. There's a strong kind of social adoption model that's built into the software design, and we'll see if it works.
All right.
Thank you, everyone.
Thank you very much.